Hello, and welcome to today's E360 webinar titled Setting the Stage for A2L Adoption in Commercial Refrigeration, brought to you by Emerson. My name is Kate Henderson, and I will be your moderator for today. We have just a few announcements before we begin. Please note that this presentation's audio is provided by phone or through your computer sound system. In addition, you may type questions that you have into the text area and hit send in the Q&A panel throughout the webinar. We will answer questions at the end and send out answers to questions that we may not get to in the coming days. If you'd like to revisit key sections of today's webinar, it will be available on demand at e360hub.com/webinars a few days after this live event. You'll also receive an email in the next few days with a link to the recorded event. Discussing today's topic will be Jennifer Butch, Director, Regulatory Affairs, Joe Summers, Senior Product Manager for Scrolls and Drives, and Mike Hill, Refrigeration System Solutions Architect. Jennifer has been involved in regulatory affairs across multiple industries for more than 20 years. In her current role as Emerson's Regulatory Affairs Director, she is responsible for managing activities related to codes, standards, and regulations. She participates in several industry organizations, including AHRI and ASHRAE. Jennifer earned a bachelor's degree in biomedical engineering from Wright State University and a master's degree in business administration from the University of Phoenix. Working in collaboration with many of the highly skilled engineers at Emerson, Joe leads new product development activities as the Senior Product Manager for Scrolls and Drives. In his role, he and his team develop variable speed compressors, variable frequency drives, and low power electronics focused on the cold chain. Joe has worked in the electromechanical engineering industry for over a decade. He earned a degree in electronics technology from Upper Valley Career Center, a bachelor's degree from University of Toledo, and an MBA from the University of Dayton. In his role as Refrigeration System Solutions Architect, Mike's contributions comprise an integral part of Emerson Solutions Integrations team in our location in Kennesaw, Georgia. He and his team are responsible for developing long-term solutions for our customers. Over a career spanning more than 30 years, Mike has worked in the HVAC, electrical, and refrigeration control industry, primarily in and around Atlanta. These include engineering, managerial, and architectural positions at Trane, Automated Logic Corporation, and QTS data centers. Mike earned a degree in electronics and computer technology from Control Data Institute in Atlanta. The webinar will now begin. I'll hand it off to Jennifer, Joe, and Mike.
Thank you, Kate. So today we're going to talk about the path to A2L regulatory approval, A2L refrigerants and some options, and then refrigerant application. As we think about the regulatory environment and the transition to A2L, one of the questions that we often receive is, why are we seeing a transition in refrigerants now? What's driving that? And the very high level answer is activity at the state and federal level, specifically California with some of their HFC regulations, followed by the US Climate Alliance, and now with the passage of the AIM Act, some federal activity. The AIM Act passed at the very end of 2020, and it has three key elements. The first is to decrease the supply of higher global warming potential, or GWP, refrigerants. The chart on the top defines the schedule of this phase down, and earlier this year, we saw a 10% decrease from baseline. This baseline is approximately 10 years old, as it was calculated between the years of 2011 to 2013. And so for the first time in January, the producers were now allowed to produce only 90% of that quantity. In 2024, we will see another step down of 60% of baseline, or a 40% decrease. So that's the most significant step that we will have in these first 5 years. And then you can see the rest of the schedule there. The second and third key parts really revolve around balancing the demand in new equipment and in existing equipment for those higher GWP refrigerants. In response to the AIM Act request to limit demand in HFCs and new equipment, AHRI, or the Air Conditioning, Heating, and Refrigeration Institute, submitted multiple proposals. On the commercial refrigeration side, the most recent proposal established a 150 or 300 GWP limit in the year 2026, largely dependent on charge size. So with the higher charge equipment having a lower GWP value, recognizing that sometimes or often the higher charge equipment leaks more. And so moving more aggressively to a lower GWP fluid was warranted. This is only for new equipment, and the definition of that new equipment can be found at the bottom of this slide. You may recall that California has already established a 150 GWP limit for new equipment in new facilities beginning this year. So that's another driver that we see. Looking at this refrigerant chart, you'll notice that the GWP values are along the x-axis and the capacity is along the y-axis. And we have a split y-axis here with 134A on the left. So your 100% capacity limit would be what you would expect with the 134A. And on the right, it's relative to 404A. So you can do the comparison depending on what your equipment is using today and look at these refrigerant options relative to the capacity there. You'll notice as the boxes indicate the specific refrigerants, and as we move from right to left, many of these boxes shift from green to a pink or even a red or an orange. This is indicative of moving from a non-flammable refrigerant or an A1 to an A2L, the pink boxes, or red being the A3 propane, or even a B2L ammonia. It's important just to notice that the ideal replacement, which Joe will talk about more in the next section, but would ideally have a similar capacity but move lower in GWP. And so the next logical question might be, why do we not see many of these A2L options in the market today? And the simple answer here is that many of our safety standards were developed around these A1 or non-toxic, non-flammable refrigerants. And so to enable the use of A2Ls and increase the charge limit of A3s, there were modifications needed to these safety standards. UL 60335-2-89 is the product safety standard. This is the equipment standard that OEMs often use when they're designing their equipment and need to seek certification and listing of their equipment. It includes mechanical and electrical requirements, just like the previous editions, but it also pulls in flammable refrigerant requirements as well. In this case, the standard defines the charge limits depending on the LFL or lower flammability limit of the refrigerant. And it's important to note that each refrigerant has a unique lower flammability limit. And it also defines the mitigations for using those A2Ls, such as passing the Annex CC test, for example. UL 60335-2-89 defined the charge limits for standalone equipment as 8 times LFL for closed appliances, think doors and drawers, and 13 LFL for those that are open. So you have open cases or other pieces of equipment, maybe where air is not restricted or trapped behind a door or in a drawer or a bin. And so this really equates to 300 to 500 grams of propane in a self-contained piece of equipment and 5 to 8 pounds for A2Ls. Remote systems can also use A2L refrigerants and may go up to 260 times the LFL, or roughly 170 pounds, so long as they use the mitigations to limit their releasable charge. ASHRAE 15 is the application standard that defines the requirements during installation. This is largely based on occupancy type of a building. And ASHRAE 15, just like the product safety standard, has been around for a very long time, but needed some modifications to allow for harmonization with the updates to the 2-89 standard, and really to allow for some of these larger charge limits. It's important to note that a lot of these changes were based on research, extensive research that AHRI, ASHRAE, Department of Energy, UL, and others have conducted over the last decade. The last piece to enabling the use of A2Ls is for EPA to list acceptable A2Ls in commercial refrigeration. A few months ago, industry was asked to prioritize their A2L options, and EPA is currently working through a draft rulemaking. The last piece of the puzzle is for the building codes to be updated to allow for use of these A2L fluids. Like I mentioned, historically, most of these codes were built around A1 fluids, as well as some very small charged propane systems and self-contained equipment. So this is the current status of the building codes, and you can see just the blue striped states are the only states that so far have allowed their building codes to be updated once those EPA substitutes are approved. So there's a lot of work to be done here, and AHRI and others are working diligently to see this process through. At this point, I'm going to transfer this presentation over to Joe, and he'll walk us through some of these specific A2L options.
Great. Thanks, Jennifer. So getting into some of the actual refrigerants, I think it's first appropriate to think about, well, what is the general applicability of A2L? So on this next chart, you'll see a very broad range. So starting on the top left-hand side, we're talking very small units, and then going over to the right-hand side, we're talking up to very large units, all the way up to 1,000 horsepower. So you kind of read this chart by looking from the very small on the left to getting into your larger stores. So on the left-hand side, you have self-contained units where you'll commonly find hermetic reciprocating compressors, really fixed speed applications up to about 3 or 4 horsepower, variable speed because of the increased speed, you can get up to about 6 or 7. At that point with R290, you start to have to duplicate circuits. So that becomes costly. So this chart was really done from a stance of total cost of ownership. So then you get into the larger systems that are usually larger self-contained systems or remote systems that are in systems that are charged out in the field. That really goes from the 0 to about 60 horsepower. As Jennifer mentioned earlier on, there's charge limits with a lot of these refrigerants depending on your LFL. So when I say 60 horsepower here, that obviously depends on your refrigerant that you're using and your charge amount that you're allowed to use. So that'll vary a little bit, but roughly speaking, you get to about 60 horsepower before you're going to have to repeat A2L circuits in order to get more capacity. So above that, especially in applications where it's not practical to use ammonia, because ammonia is actually a really good refrigerant, but it's obviously toxic. It has other reasons why you wouldn't want to have it in the back of your grocery store or around applications such as a large retail establishment. So CO2 in those types of systems seems to be the front runner. So really when we're talking about A2Ls, we're talking about this range from the very small units to the very large units in our hermetic scroll and semi-hermetic products across these applications. Increased charge limits of R290. R290 today is probably only good up to about a little over 1.5 horses, 2 horsepower, but the increased charge limits are going to let that get a little bit higher as well. But for field charge systems, especially, A2Ls are definitely seem to be the front runner from a total cost of ownership perspective. even though you will see a couple of spots in there of CO2 and things like that where people are using those in smaller systems. So getting into the refrigerants themselves. So you'll see this is focused on 404A alternatives in the Copeland product portfolio. And this is it's a refrigerant-based analysis with the benchmark being 404A on the left-hand side and everything else being a comparison to that left-hand line. So we're approving our product lines, our core product lines across the board as a Copeland brand with these three A2L refrigerants when it comes to 404A alternatives, which are 455A, 454C, and 454A. There's good reasoning behind that. We're essentially, if you think back to the slide that Jennifer just presented a few minutes ago, you have essentially a 150 GWP bar for systems that are above 200 pounds of charge, and below that you have this, for remote systems, you have this 300 GWP bar that's potentially there. So for those 150 GWP limit applications, your self-contained applications, or even some remote, you really have two options here. You have 454C and 455A. That is the focus point for us. And there's kind of a trade-off here. So if you look at 454C, your compressor capacity, you're going to lose about 8% compressor capacity. But to its benefit, your glide is going to be right around the same level as you would get with a 448A today, which is pretty widespread use today in 448A. So it's the closest to a drop-in. It's going to minimize the engineering work to implement versus other options that are out there, even though you are going to have to upsize your compressor by 8% in order to make up that capacity gap. So if that gap is a big deal to you, well, then there's R455A. So R455A gets just about the same capacity as 404A, but the downside to it is the level of glide. 22 degrees of glide likely means that you are changing your coils in your system, and it's going to require redesign work in order to implement that refrigerant. But to the positive, you will not get that loss of capacity that you'll get with 454C. In remote systems, you've got a higher GWP threshold. So R454A then becomes a pretty good option because you have that 300 GWP threshold. Assuming that everything goes through as the AHRI proposal that Jennifer showed, you're actually going to get an increase in compressor capacity. Your compressor efficiency is going to go up, and your glide is actually right at about the same, a little bit less than it would be with R448A. So in those remote applications where 300 GWP is going to be allowed, R454A becomes a really attractive solution from a total cost of ownership perspective. So those are the three that we're focusing in on. And you can see I listed a few other options on here that I'm not going to go into great detail about, but I mean, the general reason why we didn't include some of these other ones was we thought it was either going to be too much from a total cost of ownership perspective, meaning that you would have to upsize your compressor by a significant amount, or it had limitations in terms of, for example, you might not be able to use it in a low temp application or something along those lines. But if you're an OEM watching this, I would encourage you to reach out to your Copeland representative, and if you'd like to do a deeper dive into the option, because obviously we looked at dozens and dozens and dozens of different refrigerants in our evaluation to find a 404A replacement. So we obviously can share that level of detail with our customer base on an as-needed basis in greater detail. But we do have OEM samples available across the core platform today with these refrigerants. So reach out to your Copeland representative if that's something that you may be interested in. One other thing to kind of move this into the electronics section, where I'll kick this off to Mike Hill, but electronics with flammable refrigerants, there is a little bit of a difference, and I focused in on compressor electronics here, variable frequency drives, since Mike's going to be covering the latter in his section. But there are, when you're talking about electronics, such as compressor mounted electronics or contactors that potentially are in the same space as the refrigerant circuit, where there can be potential leaks there, you can't use the same componentry as you may have been able to in the past in order to comply with the new UL standards. Hermetically sealed componentry is required. You'll see on the right, we're updating all of our products to be A2L or A3 compliant across the board with our onboard compressor electronics and our variable frequency drives, as well as our contactors. So keep that in mind as you get into your A2L applications. There are some other ways to get around it. You could do system level certifications, or you could put the existing electronics in an enclosure that's certified. But at its core, the intention here is to make sure that people are aware that for A2L based systems that your compressor mounted componentry, variable frequency drives, things that may be outside of that may be in that potential leak zone of your refrigerant circuit need to be certified componentry. Again, if you have additional questions about the detail of this and what exactly is needed, please feel free to reach out to your Copeland representative. But with that, I'll go ahead and I will kick it off to Mike Hill. Mike?
Thanks, Joe. We're going to kind of jump into the controls and kind of see what's different about A2Ls and what's needed going forward. So what is different about an A2L store versus a regular HFC store? So there will be a need for a case controller with a leak sensor mounted in the evaporator area. Isolation valves that will need to be factory installed outside the case. And then on walk-ins, it'll be the isolation valves or mitigation valves will be need to be filled installed outside the walk-in case. So a couple of different things on new equipment, what will need to be installed at the OEM and what will have to be installed in the field. So go to the next slide. So let's talk a little bit about the requirements and what is needed at each level. So closed cases under 5 pounds will need no mitigation. But once you get above the five pounds, and you'll hear a couple of things mentioned, you'll hear the difference between system charge, and that will be the whole entire system, whether it's a self-contained or distributed system. Or you'll also hear releasable charge, and that is just what's released inside the coil area or inside where your two mitigation or isolation valves are located. So, so once you get to the 5 pound level on a closed case, you'll see that you will need a leak sensor and you will need isolation or mitigation valves. And then we'll move down to an open case. An open case, anything under 8 pounds will need no mitigation, but once you reach the 8 pounds of charge, you will need leak sensors and isolation valves. And then walk-ins, this is where things kind of get a little bit tricky. I've got another chart we'll show you, but on a walk-in, you will need leak sensors, isolation valves, all the time. And then sometimes you'll need air circulation, whether it's to an outside area. Air circulation on the fans, on the evaporators. Sometimes you'll need ventilation to the outside area. And then sometimes the square footage of the area or the walk-in will be enough to cover the mitigation, so you won't need any others. And then with the rack rooms, where your racks may sit, or a mechanical room or a mezzanine area, you will need a leak sensor all the time. Sometimes isolation valves, depending on the setup and the charge of the system. Sometimes air circulation, and then ventilation as well. And then depending on the square foot and room volume of the room, it will depend on what these mitigations are needed. Outdoor, oh, let's go back real quick, sorry. Outdoor condensing units, if the outdoor condensing unit is sitting outside, no mitigation will be needed. And I know we talked a little bit earlier about charge limits and things like that, but yeah, system charge on an A2L system, 166 to 170 pounds will be the max. I don't know if that number's fully determined, but as of now, that's what we've got. So a system cannot be any larger than that in pounds. You'll have to have multiple systems if that's the need. We'll talk a little bit about the releasable charge inside a walk-in evaporator area. So depending on the charge of the system, so say you've got a system with 32 pounds of charge, you go across, and then you'll look at the square footage of the room area or the walk-in area. And when you're figuring this room area or the square footage, the max height of 7.2 is the max you can use in your calculation. So if the height of the box is 20 foot, 7.2 will be the max area you'll be able to use for that calculation to figure out your square footage. So this will tell you, if I've got a 33 pound system in a 500 or 750 square foot walk-in, circulation is all that will be needed. If you move to a bigger box, more charge, room volume may be enough, may need ventilation, or it may be out of compliance. So that's just one thing in determining, what mitigation is needed, the size of the room and the charge. We'll go to, this is a rack room, same type chart for the rack room and condensing units. If I'm in a mechanical area, whether, ventilation is needed. So if I'm at that max charge level of 166 and my square foot room area is, 500 square feet, I'm going to be out of compliant. I'm going to have to put it in a larger area. And then I'm going to have, ventilation if I'm over, the 33 pounds of the M2 charge level. So us at Emerson, we're doing several different sensor evaluations for several different applications. So currently we have sensors that do have A2L refrigerants as a selectable refrigerant, and that is the MRLDS 450. And this is, so it'll give you a sensing range of 0 to 1,000 ppm. It also has some relays for alarming that you can send external relay outputs. It has Modbus communications, but included in this, where we do not see that this is going to be the perfect need for a case. It's really too large for a case, and it includes extra hardware that's not needed, and it cannot do the control mitigation. So you would still need some other logic built into that controller to do A2L at the case level. So we are working with several, suppliers to try to figure out what's the best need, what are the options the OEMs and customers are looking for leak sensing. So we've got three options here we're kind of examining and looking at and testing. So we have a communicating version, which will just read a 0 to 100% LFL, and it'll communicate over Modbus to a controller or a supervisory system for that case. And it will tell it, what level my LFL is at. Am I at a 10% level, or are we at a 5% level, whatever the case may be, 25% level. And then it'll also need additional I/O to control the mitigation or the valves to shut down the refrigerant at the case. So these sensors, all of these three I'm going to talk about, the refrigerant types are preset at the factory, so you'll order them by the refrigerant or the A2L refrigerant that you're using. The other low tier that we call this kind of our tier 1 leak level sensor, it will have a digital output that will close when I reach 25% LFL. So this is pre-calculated in the sensor based off the refrigerant. When I reach the 25% LFL, a contact closure will close, send that closure to the case controller, and close off the mitigation as needed. And then we've got an upper tier, which is an analog signal. So it will read the 0 to 100% LFL. It'll send a variable signal back to a controller. It's telling me what level is that I'm at, so I can do a pre-warning to say, before something actually trips, I could get a signal to my system or my controller that says, hey, I'm at 10%, I'm getting close to tripping off and shutting down the system. So it could give a pre-warning. You could generate a light or some type of message out through your supervisory system that would give you some type of warning. So these are the ones we're evaluating and what we have now currently available. So we'll talk a little bit about the A2L logic. So this system would be the digital sensor application. So I would constantly be reading the sensor at my controller level. Once I got greater than the 25% LFL, I would close my isolation valves. I would turn on the fans for circulation. I would turn off any defrost heaters that may be on. I would also turn off the refrigeration or compressor. I would alert the user that I have a leak and mitigation is enabled. And then I will set the alarm to true, and I will lock all this out till the unit is out of danger. There's no more leak red, and also there is a reset level that'll have to be done to turn everything back on to a normal state. So it will remain in a lockout till the alarm is triggered no more, and then it will say, hey, I've been without a leak for this amount of time, and I will send the system back into normal. I also have an A2L logic for the sensor with an analog value. So once I get to a 1% LFL or less than, greater than 1, less than 5, these will be adjustable LFL levels you'll be able to set in the controller. I can say, hey, I've got a warning, alert, I've got a small leak, send a technician to check this out before it trips off, whatever the mitigation or whatever the level of severity you want to raise it to. And then once I get to the 25% LFL that you set, then I'm going to go back through my, closing my isolation valves, turning on fans, turning off heaters and compressors, making sure everything is triggered. I've set the alarm to the supervisory system. We haven't clearly come to an understanding if there will need to be a light or something at the case level to say, hey, this case is tripped off. I know there'll be a message on the display at the case, but I'm not sure on exactly what that need's going to be. And then same thing, once everything is back to a normal state, I've been without a leak for whatever the predetermined, 12 hours without a leak or whatever it may be, I will initiate, back to normal level. So that explains a little bit about the logic and the controller, kind of what we're looking at, what we're testing. So us at Emerson have come up with kind of 3 different tiers and using some of our existing controllers and some of our new controllers to say, all right, what will the customer be looking for? What will our OEMs be needing? So we've got our current XR lines that will just read the digital input. They won't be able to read an analog input. So we will use the first level sensor with digital control to say when I'm at 25% LFL, I will trigger a digital input to the controller, which will shut off my mitigation and safety valves and turn off compressors, turn on fans for circulation. And then with our current offerings on the XM 670, 678s, and 679s, we'll be able to read a analog signal where I could give you some early warnings and then also do my mitigation with my safety valve shut off and fan control and alert my supervisory systems as well. And then we have the premium, kind of our tier 3, using the CC200 case controller, which will read a 0 to 10 volt signal. It will also do some smart data and analytics that can be pushed automatically up to a cloud solution. So that kind of gives you what the smart data is. It'll also provide the early warnings, shut off my safety mitigation valves, and alert the system supervisory system as well. So this is all based off of variable signal-based LFL, and the tier 1 just trips at the 25% local, low flammability levels. Things we're not sure about, we've allowed extra outputs for local alarms, like if you want to use a light and then also a input for a silence button or a reset. So those things we're still kind of working our way through. And then at our Helix Innovation Center in Dayton, Ohio, we are doing an A2L testing. We've got it set up, testing, allow people to come in and adjust it, play with it, see how it works. But we have a new A2L system with 2 cases installed. We've got a case controller doing regular control. And we've added, been testing the leak sensors that we have, reading the sensor level, kind of here's some of the logic we've used. So at 5% LFL, we've set this up. The analog input will send an alarm, an advisory or early alarm. If once we get to the 25%, which is 2.5 volts from the controller, from the sensor to the controller, the relays close, valves close, and then we alert the alarm. And then we have run these tests through. We're working on, kind of narrowing down our sensor selections now, and hopefully be able to allow, OEMs samples for testing and provide. We have data that we can provide as well on our testings here at the Helix. But that's kind of where we're at. We look forward to working with you guys and seeing what your customers or what you are thinking and maybe what your needs are to help us, kind of close the gaps here going forward.
Okay. So at this time, we will now be transitioning to our Q&A portion of the webinar. Brian Beinasek will be moderating this section, asking questions for Jennifer, Joe, and Mike to answer. So I'll hand it off to Brian.
All right, thanks. We got a lot of good questions. We'll try to answer as many of them as possible. The first question is for Joe. It has to do with ammonia refrigeration. And the question was, do we see a future for medium-sized ammonia chillers installed outside of buildings? And Joe, you might have to unmute yourself.
I mean, I don't see why it wouldn't be possible. I guess as long as it's outside of the building, it kind of falls under a different set of regulations than what we were targeting for today. We were really focused in on 60335-2-89 for today's presentation. Yeah, I mean, for a chiller application in an outdoor environment where you're not really worried about interacting with people or things like that, I guess where I would go is the benchmarking it versus your A2L options that you potentially have available there too, because obviously you could use an A2L in some of those applications as well, depending on the size that you're talking about. Yeah, I don't know that we see it as a major driver in the core piece of our business for an ammonia outdoor unit and a medium-sized chiller. But it certainly is popular for larger systems when you get up into the couple hundred horsepower type of unit. So, yeah, I mean, depending on the context, I mean, ammonia is a very good refrigerant. It's really just figuring out where and how to use it and falling under the appropriate regulations, which does fall out of 60335-2-89.
Thanks, Joe. That actually sets up the next question, which is for Jennifer. You mentioned 2-89 safety standard. Jennifer, the question is, how do these safety standard updates kind of set the stage for wider refrigerant approvals?
Thanks, Brian. So really updating these safety standards was the first piece. So ASHRAE 15, like I mentioned, is now being updated and should be updated this month to match the 2-89 safety standard. So really the product safety standard was the first part, and then EPA could not approve any A2L refrigerants unless there was a product safety standard that outlined the safe use of those refrigerants. And then building codes obviously can't be updated without product safety standards. So really the first piece was to update the product safety standard, and then everything kind of builds from there.
Okay, good. The next question is for Mike, and Mike, you might have to unmute yourself, but it was about calculating the charge limits when you're talking about that. So when you're talking about a walk-in, say 20 by 20 by 20, and you have that maximum height of 7.2 feet, do you first calculate the volume of the walk-in and then divide by 7.2, or should you just calculate the square area and then multiply by an assumed 7.2 foot height?
Yeah, you got to assume the 7.2 in your calculation. And that was something that was determined that would be the max. And I do not know the reason why they chose, the 7.2.
So it's kind of a second part to that question. If you were talking about calculating charge limits for, say, a display case inside a large retail store, would you also have to assume that 7.2 foot height, or would the calculations be done differently?
No, it'd be done differently in that area, okay, because you got the releasable charge at the coil there, being the different level.
Got it. All right, thanks. Joe, a question about A2Ls. You showed an example at plus 10 degrees Fahrenheit saturated suction, which would be perhaps considered medium temp. The question was, will A2Ls also be approved for low temperature applications?
Yes. So the one example that I had there was it was medium temp, but at low temp applications, any of our low temp models today are being approved for the same three refrigerants: R455A, R454C, and R454A across the board. And your performance is really similar, even at the low temp condition. I mean, we could dive into those details in a more specific discussion if people want to talk about that. But I mean, really, like things like your glide are going to get adjusted a little bit, things like that. But same three refrigerants across all of our low temp models will be approved as well. Is the answer.
As an add-on to that, I just make a comment. There was some questions about our selection software, our product selection software, and Emerson's online information. Are those programs being updated with the newer refrigerants that we're talking about? And I can say, yes, they are. They're being updated constantly. So if you use that software, continue to get it updated, you'll get the new models. I didn't know if there was anything you wanted to add to that.
No, well, I mean, just, I guess to build on that a little bit, you'll see, if you go out there now, you'll find across our scroll platforms that you'll find the data available. You'll just want to type in your Google search Copeland product selection software, and you'll see it. It's really easy to download and very simple to use, and you'll be able to pull out performance coefficients and all the detail you would want on these new models.
Okay, Joe, thanks. Question for Jennifer regarding California Air Resources Board. Do we know when we're going to know if the charge limit per circuit is going to be that 50 pounds or 200 pounds for A2L refrigerants?
So California's regulation is a little different. They chose, because they've already adopted SNAP 20 and 21 at the state level, and they did that back in 2018, I believe, effective in 2019. So they already had pretty good transition for a lot of that equipment. And they really focused on the larger than 50 pounds because they already have a database that allows them to monitor any equipment that's greater than 50 pounds. It already has to be registered within the state. So when they rolled out their regulation, they based it on that. Now, the AIM Act does not contain federal preemption, so there's no requirement that California back off of their regulation and follow the federal regulation. So we don't really anticipate that California would change anything, even if the federal government pushed something out. Now, if the federal government pushed something out that was more aggressive, then the states would have to at least meet the federal regulation, but they could go above and beyond. And I think there's a handful of states that we believe are likely to continue to regulate HFCs above and beyond that federal level.
Okay, thank you. Jennifer, another question came in for you. This presentation was structured and we talked about 2-89. Are we going to be doing a presentation on UL 60335-2-40? Are we going to have a webinar on that in the future?
Well, we might have another one. I don't ever know exactly what the forecast is for the future, but I would say that we have presented on 2-40 several times. And so I would just encourage folks to go out to the E360 hub. There are several regulatory presentations out there where Rajan Rajendran and myself have presented more holistically on the regulations for the entire webinar. So you'll get more detail through those webinars.
Perfect, thanks. Mike, a question came in for you. For the motors used in these A2L systems, do they need to be intrinsically safe motors?
That I do not know the answer to, because I know they'll be pulling the A2L across those. So I'll have to find that out for sure. I do not know that answer.
There's a lot of great questions coming in. Any we don't answer today, we will get back with you, in the next week or so in writing. So we'll be researching some of these because there are some really, really good and tough questions in here. So there's this question about cascade systems, and this is probably appropriate for Joe. So, today R404A, R448A, if they need to be replaced as the high stage refrigerant of a cascade system, what kind of what do you see for the future for those type of systems?
Well, I mean, cascade systems, typically are going to be of a larger charge level. So I think that they'll end up being a split. Some of them will want to go towards retrofits with something like a CO2 type of a system, right? But others will end up being more decentralized systems, and they'll actually just end up going with something along the lines of an A2L, where they end up with more systems rather than one centralized system and a normal cascade. But that being said, and to the degree of that split, it's hard telling. It's going to be tough to justify a lot of, unless you're ripping out everything and starting anew. The system that's there is the system that's there. And the new regulations are for new systems currently. A2L is not really a retrofittable option. At least not today, maybe some point in the future. But as of today, I would think that most of the systems are going to keep on where they're at for the time being. And as they rip out and replace, you're probably going to see them split into either a large CO2 system or a decentralized A2L system.
Okay, good. Thanks. Several people asked about whether this presentation would be available, if the recording would be available, and I think Kate mentioned early on that we will be sending out a link soon that will have a link to this recording, the video, and you'll be able to download the presentation. I think we're going to do one more question today during this webinar, and this is for Jennifer, and it's, how can I learn more about flammable refrigerants?
So lots of great resources out there on flammable refrigerants. The Emerson E360 Hub, as I mentioned, has a lot of articles as well as past webinars and other information, white papers. AHRI also has quite a bit of information in their Safe Refrigerant Transition Task Force section. So you might want to visit the AHRI website. I think all of the OEMs will eventually be putting out information on the specific use of their equipment and transition to lower GWP refrigerants, including A2Ls. So there's just a host of resources out there for you to look at.
Jennifer, Mike, Joe, thank you for answering those questions. I'm going to put this back to Kate now.
Awesome. Thank you again, Brian, for moderating the questions today. And thank you, Jennifer, Joe, and Mike for presenting today. So that's all the time we have for questions. Thank you again for your participation. Like Brian mentioned, any questions that we were unable to answer during our time today will be sent out directly to the asking individual in the coming days via email. As a reminder, a few days after this live event, you can access this presentation on demand or review previous E360 webinars at e360hub.emerson.com/webinars, and you'll also receive an email in the next few days with a link to the recorded event. If you want to subscribe to our monthly E360 newsletter and access all of our E360 content, visit e360hub.emerson.com. Please note, a survey will appear after the webinar has concluded today. We would really appreciate your response and hearing your feedback. On behalf of Emerson, thank you for attending today's E360 and will be available soon for our next upcoming webinar. We hope you can join us again. Thank you.